I'm just going to test the volume on this. So you can just ignore it for the moment. I'm just testing the volume. Okay, don't want that one.
Hi everyone, my name is Nicole Stott and I'm a flight engineer with Expedition 20 on the International Space Station. And we're here today with you on the International Space Station and the Japanese Laboratory Module.
Hi, I'm Bob Thirsk. I'm also a...
Okay, so this is a little video on mass and weight and the difference between mass and weight. So we're going to be on page 14, page 14. Page 14, 14. And don't worry, if you're still writing your quiz, don't worry about it. We'll be actually filling it in after we've finished watching it. So if you miss anything, no worries. Page 14. Hi. You already did it. Well, then you just get to sit back and relax. Okay. Yeah, we're going to hit the lights. Okay, so these are some people who are up on the International Space Station. Okay?
flight engineer aboard Expedition.
Hi everyone, my name is Nicole Stott and I'm a flight engineer with Expedition 20 on the International Space Station. And we're here today with you on the International Space Station and the Japanese Laboratory Module.
Hi, I'm Bob Thirsk. I'm also a flight engineer aboard Expedition 20. The topic for today is weight versus mass, a heavy-duty concept.
So what is weight? Weight is the vertical force exerted by a mass as a result of gravity. Weight also means the strength of the gravitational pull on the object. That is, how heavy is it? Weight is dependent on gravity.
On Earth, in a 1G environment, an astronaut in his spacesuit would weigh 360 pounds. On the Moon, in 1/6 Earth's gravity, the astronaut would weigh 60 pounds. In orbit, he would weigh 0 pounds because weight is dependent on gravity and the effect of Earth's gravity is not observed.
Using more physics and mathematical terms, weight is defined as the force with which a body is attracted to Earth or another celestial body, equal to the product of the object's mass and the acceleration of gravity. So in equation form, gravity equals mass times acceleration due to gravity. On Earth, that's 9.8 meters per second squared.
But what is mass? Mass is the property of a body that causes it to have weight in a gravitational field. The mass of an object is not dependent on gravity. Mass is the amount of matter in an object. Bodies with greater mass are accelerated less by the same force.
If we use the same force on these two animals, the elephant, which has a greater mass, is affected less than the mouse, which has much less mass.
And what is gravity? Gravity is a force that governs motion throughout the universe. It holds us to the ground. It keeps the moon and the station in orbit around the Earth, and the Earth in orbit around the sun. It is best described as the attraction between any two masses, most apparent when one mass is very large, like the Earth. The acceleration of an object toward the ground caused by gravity alone near the surface of the Earth is called normal gravity, or 1g. This acceleration is equal to 9.8 meters per second squared, or 32.2 feet per second squared. If you drop an apple on Earth, it falls at 1g. If an astronaut on the space station drops an apple, it falls too. It just doesn't look like it's falling. That's because they're all falling together. The apple, or the onion, the astronaut, and the space station, all falling together.
Well, what is microgravity? The International Space Station and us astronauts aboard are traveling at approximately 28,000 kilometers per hour, or 17,500 miles per hour. And we're essentially falling around the Earth, creating weightlessness. The weightlessness that is felt in free fall on a ride at an amusement park or on the International Space Station when it circles around the Earth is microgravity. Objects in a state of free fall in orbit are said to be weightless. The object's mass is the same, but their weight would register 0 on a scale. Weight varies depending on if you're on Earth, the Moon, or in orbit, but your mass always stays the same.
Sorry, I'm not.
The first thing that Koichi and I would like to do is demonstrate that we're actually on board the International Space Station and we're in a weightless environment. So let us show you a few little tricks here that'll make that point.
Okay, here we go.
Now, I missed that, sorry. So we're going to go back. What were they doing?
Actually on board the International Space Station and we're in a weightless
Arm wrestling?
environment. So let us show you a few little tricks here that'll make that point.
Okay, here we go.
Oh, they're just having fun. Okay, cool. I know, right? Oh, so you can turn it on and turn it off kind of thing? Yeah. Yeah. In order to actually get gravity, they would need to basically spin it so that you would provide a force that's similar to gravity, but it wouldn't be really gravity. Yeah. Yeah.
I'd like to have an arm wrestle with Koichi. Let's see what happens.
Okay. So,
Have we seen the arm wrestling yet? No. Okay. What do you think's going to happen? Nothing. Okay. Let's see.
okay, here we go. You can float. This is great, actually. Okay. And then smaller.
One of my favorite Japanese sports is sumo wrestling. We're going to try to sumo wrestle. Be careful.
So, out of those two, which one do you think has more mass? Let's watch it again. Which astronaut has more mass? Let's go watch them do that again. Do their sumo wrestling. The far guy. Okay, so this guy had more mass or less mass? Less mass. This guy has more mass. Yeah. Why? How do we know? He didn't move as much. It's like when you push the elephant doesn't go far as the mouse if you push it with the same force.
That is super.
The somersault.
Okay, Nicole, show us your stuff. Where'd she go? Come back. It's Superwoman.
Okay, and that is it. So let's just go through here and make sure that you got everything. All right, and we'll talk a little bit about it as well. So what do we call a vertical force exerted by a mass? We call that weight. Now, do you remember the unit for force? The unit for force is the Newton. N. If weight is a force, what is the unit for weight? So the unit for force is a Newton. Weight is a force. Newton. Okay? So the unit is the Newton. Weight depends upon, it does depend upon gravity, but gravity depends upon the mass. Did they say gravity? Oh, okay. Let's put, you know what? You know what we can do? We can put weight depends upon gravity, which depends on mass. There, that's a better answer. So on Earth, did anyone catch how much an astronaut weighs? 360 pounds. But on the moon, an astronaut weighs 60 pounds. Can you guess the mass of the moon relative to the mass of the Earth? The mass of the moon is mass of the Earth. Now, this requires a little bit of mathematical thinking, so I don't expect everyone to necessarily get this, but I would like you to think about it for a moment, have a chat with your neighbor. So their mass went from 360 to 60 as they went from the Earth to the moon. And gravity depends upon mass. So do you think the mass of the moon is bigger than the Earth or smaller than the Earth? It's smaller. Yeah, if we go divided by 6, 360 divided by 6, we get 60. So what fraction of Earth's mass is the moon's mass? Yes, 1/6. Okay, I'm not going to make you like repeat that on a test or anything, but that's the kind of thing you can expect as you go into higher levels in science, is that sort of proportional reasoning. Yeah, does it make sense now? Yeah, okay. Now, on the International Space Station, an astronaut weighs about 0. All right. What was the equation for gravity? Mass times acceleration, yes. All right. And what is the gravity on Earth? It is 9.8 meters per second squared. Now, a lot of the time, just to make the math easy, they'll say that's approximately equal to 10 meters per second squared. Now, do you need to know that number? No. Nobody's going to make you memorize that, okay? The whole purpose of this is to say, when the astronaut went from the Earth to the moon, did their mass change or did their mass stay the same? The mass is the amount of matter. Did the amount of matter in the astronaut change as they went from Earth to the moon? No. Do you guys know what these 3 little dots mean? Dot, dot, dot in a triangle? Ha, triangle dot. Okay, I'm going to teach you what they mean because they're really, really useful in science and math. Dot, dot, dot means therefore. Okay, and I will use it all the time. Okay, once you get into some science, people start using it a lot. Okay, so that's going to be a really useful symbol for you. Dot, 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 therefore. And if you're not with us, we are on page 14, 1-4 in your book. Okay, page 14. All right. So mass is the amount of matter, therefore, mass does not change as you go from the Earth to the moon. And that's the big takeaway from this, is that as you go from the Earth to the moon to the space station, your mass would not change. You would have the same amount of matter in you no matter where you are. But what would change? Gravity changes, and therefore your weight changes. We tend to use the words weight and mass meaning the same thing in normal everyday life, but in science, they mean different things. Okay, in science, mass means just how much stuff is in whatever it is, but mass is how much gravity is there on that stuff. Weight is how much gravity there is. Mass is how much stuff there is in it. Okay? So we could just put that up at the top if we wanted to. Weight is how much gravity there is. Mass is how much stuff there is. So in science, those mean different things. Mass is how much stuff there is. It's the amount of matter in an object. Okay? When I say stuff, I mean matter. Just making it a little more user-friendly there. Okay. What is the property of a body that causes it to have weight? Yeah, I heard it somewhere. Somebody said it. Mass. Yeah. If you don't have mass, you're not going to be affected by gravity, which means that every single object is going to be affected by gravity because it has matter in it, which means it has mass. But if I had light, do you see the light shining from the light bulb up there? Is it falling to the ground? No, and that's because it does not have any mass. Okay? Are the sound waves coming out of my mouth falling to the ground? No, that's because they don't have mass. They contain no matter. So which one does not depend on gravity? Is that your mass or your weight? That's your mass. So that one is not dependent on gravity. Mass is the amount of what in an object? Matter. Yeah. And what do we call the force that governs motion throughout the universe? Gravity. Gravity is best described as an attraction, a pulling together between any two masses. So is there gravity between me and this pen? Yes. Yes. But the pen, how much mass does it have? A teeny bit. How much mass do I have? A lot more. But compared to the whole Earth, how much mass do I have? Not a teeny tiny bit, right? Compared with the Earth, I weigh nothing. Like I've got no mass. So when this pen has a choice between me and the Earth, it says Earth. Because the Earth has so much more mass. So you have like bigger than space. Yeah. Yes. Exactly. Right? If you just get big enough, then people will gravitate towards you. Yeah. So I would have to weigh more than the Earth for everything to move towards me rather than the Earth. Okay? So I would almost have to be like a little black hole, Ms. Spence. Yeah? Sucking all matter. Okay. Near the Earth's surface, normal gravity is just called 1g. 1g. How many meters per second squared is that? 9.8. And you don't need to know this number, but I find it kind of fascinating. In the International Space Station, the astronauts aboard and the station itself and the astronauts aboard it are traveling at approximately 28,000 kilometers per hour. That is so fast. Did it look like they were traveling that fast? It didn't look like they were moving because they were moving at the same speed as the space station. Yeah? So even though they were moving super, super fast, it looked like they weren't moving at all because the space station was moving at exactly the same speed. It's kind of cool. It's like when you're in an airplane. You don't look like you're moving, right? But you're traveling at like, I don't know, 400. I know what you mean. When it's going the opposite direction?
I mean, same.
Same direction?
Yeah.
That would be like, it's because of the distance. You know how things that are far away look a lot smaller? The distance they travel also looks a lot smaller.
Yeah.
Yeah, so I think that's what that is. Yeah. Okay, weight varies depending when you are on the Earth, the moon, or in orbit, but what always stays the same? Mass. Okay? And we're going to leave that topic for now. We'll come back to it on Monday because we're going to be doing some spaced repetition. No pun intended. Spaced repetition. Sorry. Okay. I actually wanted to go through one thing with you. Oh no, I'm going to do it next week because I got a whole bunch of people away. So we'll do it next week. So we are going to take a look now at quad beam balances. This is on page 36 because next week we're going to do a quad beam balance lab. Let's do the first one together, all right? Because I know there were a couple people who were away for when we did a triple beam balance. So let's do this together. This one would have a mass of 100. This is page 36. This would have a mass of 100 and how much? 182. Okay, so 182. And then this one is tricky, okay? I'm glad we came across this one together because it is tricky. It is 0.3, okay? And if you were to write 182.3, and if I said you're measuring a rock and you wrote mass of rock equals, and you wrote 182.3 and you wrote grams, you would get 1, 2, 3 out of 4. Because you're missing the estimated numbers. Okay, now, this one is really tricky because we're exactly on the 3. You might think, it's just going to be 182.30 grams. But we have a problem. Because on a quad beam balance, what are each of these little measurements worth? So this is 0.2, this is 0.3. Each of these are 0.01. So you must estimate to 0.001 place. So you're estimating to 3 decimal places. Yeah. So that's not going to be 182.3. It's not going to be 182.30. It's going to be 182.300. But if you find that really tricky, remember, you can still get 3 out of 4 for just getting the number correct, okay? And writing what you're measuring and the units, okay? So I'm going to get you guys just for the next few minutes. Oh, yes. And for the number of sig figs, that would be one. Oh, what's happening here? 1, 2, 3, 4, 5, 6 sig figs. Yeah. And remember, counting the sig figs is optional, but you can get enriched credit for that. Also, you are asked, no, you're not asked to do any of that. That's good. So good. Excellent. So you're going to try page 37. No, 37. 37. If you have extra time, you're going to do 38, but 38 is going to be for homework. Okay? So do page 37. Folks, if you finish pages 37 and 38, you can do some of the enrichment work. Okay. Yeah, just a little. Yeah, perfect. Yeah. Yeah, no worries. Oh, hang on. No, it's not 0 because it's 1. Oh, right. Yeah, so it's not. Yes. Just the last one. Just walk just the last one. Because you know you're yeah. Yes. So it's yeah. I think I didn't want to do that. That's okay. Your number can be close and you can off by a little bit fast.
No.
Close. When you are checking your answers, there's actually answers on page 38 at the bottom. You can be off by a little bit because remember that last digit is estimated and my estimate might be just different than yours. So as long as you're within 0.2 or 3 or something, you're good to go. Okay. Yeah. We have to do something else and then we got to do something else. That is, yeah, we might go. Okay, anyone got any questions they'd like to ask about that? Let's see. Okay, don't put away, we're not done yet. We got like another half hour almost. We're gonna learn other stuff.
Oh.
Yeah, we're not just gonna like learn and then be done for like the half an hour. Okay, so the next thing we're gonna do is we are going to take a look at page 53, 53. 53. Okay. Did you guys do the scientific method last year?
Yeah.
Did you do scientific method in elementary school at all? No? Okay, that's all right.
But you asked, we did it last year, I did, but I don't.
But you don't remember it, and that's okay. That's why we're doing it again this year. Okay? So this is page 53.
It is hot.
What is the scientific method? Well, it is a method, shockingly, that is used to find answers. And if you're like, what page are we on? We're on page 53, 53. So we use it to find answers to the questions about the world around us. Is there only one single scientific method? No, there's actually a variety. Some versions have more steps, while others may have only a few. However, they all begin with the identification of a problem or a question. This is page 53, 53. And how do you come up with these questions? Well, what do? You just kind of look around, make some observations, and you're like, why does that happen? Why is the sky blue? What would happen if we did this or that. Okay, so that is how it starts. And this scientific method provides us with an organized method for conducting and analyzing an experiment. Do you remember the word hypothesis? Ooh. A hypothesis is an educated guess, yes. Based on your observations and your knowledge of the topic. So what you might want to do before you make your hypothesis, you might want to do some research, okay? Do you guys know what data is? Data is just information that you gather during an experiment. So data is information. Hypothesis is your educated guess. I do not need you to write your hypothesis in an if-then format. I don't know, did your teacher last year make you write if-then? Okay, I'm not as picky, okay? If you want to write it as if-then, that's great. If you don't, that's fine. So we're going to list all the things that go into the scientific method. What do we have to start with? And this actually happens before the little box here. How are you going to come up with something you want to study anyway?
Think about it.
Sorry? No, I thought you were saying something. Think about it. How would you think about it? What would make you think about it? Your brain, yeah, but what to have an idea in the first place. How would you get an idea for anything? By looking at it. You would need to make some observations. So step number 1, make some observations. Observe the world. Yep. Above, because this is going to be number 2. I really need to rewrite this worksheet, but because it's the first unit, I print it really early. And so I haven't rewritten it in a long time. So I need to really rewrite it. So I need to put a little star here for myself and say fix, because it needs fixing. Observe the world. All right, you're like, oh, that's interesting. And when you observe the world, eventually you're going to say, And what is that Question. That is a question. Or a problem. Now, if you have a question or a problem, you need to think, what do I think will happen? What do we call that? That is our, you can call it a prediction, you can call it a hypothesis. I know some people get really wound up about the difference between a hypothesis and a prediction. I'm kind of like, you know what? Either can be good. So we're going to call this a hypothesis. And that's step number 4. What happened to step 3? If you want to be really, intelligent about this, I mean, you could just skip straight to step 4. However, you could do a better job with coming up with a hypothesis if you do something first. What might you do to try and answer your question intelligently? You could ask someone. What else could you do? You could search it up. What do we call any of those things? Do some research. So that's going to be step 3. That makes your guess educated rather than just a guess. The next step is, well, you've got a hypothesis. How are you going to test it? What are you doing there if you're deciding how you're going to test it? You need to be actually doing the test to get some data. You need to create what? You need to create an experiment, design an experiment. Yes. There's other ways of doing science. You might do an observational study where you just go and look at things and count them, for example, right? You might just go gather data and then analyze the data, but we're going to just talk about if you're doing an experiment here. You need a procedure that is going to provide a reliable experiment and addresses any safety concerns, okay? Because you can't be like, I want to test if nuclear bombs will kill a whole bunch of people, because that would be horrible. Yes, that would not address any safety concerns. That would be just awful. So obviously we're not going to have issues like that, but we might have things like, oh, I had a student who wanted to do an experiment and they were going to be working with 10 molar hydrochloric acid. That's really concentrated. Normally students work with like 0.1 concentrated. This was 10 concentrated. So we said, no, you cannot do that in the school, right? Because, pardon me? Yeah. I actually had a student do that this year. We told them if they wanted to work with anything that concentrated, they needed to go find someone else who's not the school, because the school doesn't want to get sued. So they're working with somebody up at SFU. So they are trying to extract colchicine from chitin, which is part of the shell of crabs, I think. So they're extracting something from a compound from the shell of crabs, and that chemical does something, and they're testing what it does. But in order to extract it, they needed this really concentrated acid.
We have it here.
The chitin stuff?
Yeah.
They had to go and get crabs shells and
Oh, wow.
crush them up. They had to grind them up, and yeah. So they're quite involved in this whole thing. All right. Follow the steps in your procedure to perform your experiment. So basically, do the experiment, collect the data. Record results. Then you're going to look at your data. You're going to say, is my data any good? Did I do a good job with it? So you're going to say, you're going to analyze your data. You might organize it in a table. You might graph it. Organize it, graph it. You might do some math with it. If you get to grade 11 or 12, or if you're advanced in math, maybe even grade 10, you can take a statistics course here, which is all about analyzing data. Yeah, which is actually really, really an interesting field. So if you're into math, statistics is a really neat course. If you're not into math, that's okay. All right, and at that point, you're gonna say, does my data actually look like it's meaningful? Is it inaccurate, or was my experiment flawed? Did I discover something along the way where I'm like, oops, I should have done this instead of that? if that's the case, if your data was inaccurate or your experiment was flawed, you need to go back. Okay? So if you don't get meaningful results, you need to go back. Does that mean that you had to prove your hypothesis correct? Or is it okay for your hypothesis to be proven wrong? Totally okay for your hypothesis to be wrong. That is a valid result. That's not the right answer. Let's go look at a different one. Okay, that's totally good. And then finally, actually not finally, there's going to be another step after this. You are going to write a conclusion that summarizes the important parts of your experiment and the results. So that is, you're going to do your conclusion. And then you are going to report to others. So we had what? 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Communicate your results to others. And along the way, there's going to be a lot of repeating of experiments. Okay, you'll repeat the experiment. Somebody else will try the same or a similar experiment to see if they get the same or similar results. And if they get different results doing the same experiment, you can say, uh-oh, something wrong with the procedure here. Where do we need to fix it? Yeah? At any rate, that's basically how science is done. So when those people on the internet are like, I did my own research. I did my own research. I went and I read Google. I went on ChatGPT and it gave me an answer, right? I read it on Wikipedia, right? Or best of all, I read it on a forum, right? I was on Reddit and somebody said, that's doing their own research. A lot of people are like, I did my own research. That's not doing your own research. What you want is if you were to actually do your own research, this is what you would be doing. Now, most of us don't have the time or the availability, like we don't have the equipment to do all of this stuff for everything we want to know about. So we have to rely upon reputable publications. So we would want something like the Journal of Nature. Okay, I actually have a student who is published in the Journal of Nature. It was very exciting. I ran into his mom when I was going for a walk one day, and she's like, do you remember, you're Miss Spence, I remember, do you remember Sean? Blah, blah, blah. He's at the University of California, University of Southern California, and he got published in the Journal of Nature, and I forget what he was doing, but it was pretty awesome. The Journal of Nature is a top-notch publication that has many, many other scientists reading the work, looking at the data, seeing if they actually did the analysis correctly, looking at other similar studies to say, is this actually good? So if you are doing your own research, those are the kind of publications that you should be looking at, not, I Googled it. And, this trad wife mom from Utah says that this is true, right? You want some actual scientists to have done the work. Yes. Yeah, absolutely. Okay, so that is it for that. And class is over today at 1:40. So we have 10 minutes left. What we're going to do with those 10 minutes is we are going to go to page 58 and 59. Do you want me to read the first story out loud? Or do you want to read it yourself? Nobody cares. Okay. So I'm just going to introduce this to you, and then I will read the first story out loud so you get an idea of what you're doing, and then you can do both pages 58 and 59. So for each scenario below, you are going to identify the 7 steps of the scientific method that are listed down here. So you are going to identify the observation the person made, the question that they came up with, the research they did, the hypothesis they came up with, the experiment they performed, the analysis they did, and the conclusion. Is that all the steps of the scientific method? No. Is this a kind of question you might end up with on a quiz or a test? Yes. So it's very unlikely that I will say, please give me a definition of a hypothesis. What I might do is I might give you a little story like this and say, please identify the hypothesis. So here's the first little story. This is on page 58. On a walk in autumn, you notice that the leaves of the trees are changing color. That's what you notice. What makes that happen? You wonder. You wonder. You think back and you remember all that you've learned about what makes tree leaves green. And you remember that trees use sunlight to make food. You then predict that if there is less sunlight, then the tree's leaves will change color. You decide to test this by putting one young potted tree outside, exposed to normal light and dark cycles, and one tree in a dark room where it receives no sunlight at all. After 1 week has passed, you check the trees and see that the tree outside has more green leaves than the tree placed in the dark room. Based on this information, you decide your hypothesis is correct. Based on that little story, you are going to identify what was the observation, what was the question, what was the research, what was the hypothesis, experiment, analysis, and conclusion. Then you're going to do the same thing for page 59. You might be able to finish this before class is over. Sorry? This is also homework. So homework is pages 37, 38. Maybe you've already finished that. Pages 58 and 59. Might be able to finish that right now. You've got 8 minutes. Okay. Or you can not. Yeah, no, it's all good. So you can go right now. I would thank all the parents once again for being an awesome class. I've enjoyed working with you this week, and we'll do more next week. Yay! Having a fabulous weekend. Thank you so much. Don't forget your phones. Yeah. Okay.